Assignment number 19, we're actually going to learn something that's probably new and really important in this one. So I'll tell you when we get there. But let's get going. So it's to do with this thing here. So I'll just do the first bit first. A point has coordinate this and this. Whenever you're given something like this, just put down a quick sketch. So I'm going to put down this point roughly where it might be, this point roughly where it might be, -4 plus 4. And then you've got a variable point at xy. So let's just put that down somewhere. Let's put it down there, xy. And it moves on a path such that the distance a to p is twice the distance b to p. So let's look at the distance a to p. That needs to be twice that distance. Okay, so this looks okay, right? So that looks roughly twice that distance. So at this point it seems right, but it's a variable, of course. There's a bunch of places it could be. So it could maybe be there. And you know, this means AP is twice as long as that. So this distance is twice as long as that distance. So this looks right. This looks all right, maybe. So does this. That looks roughly twice as far. So it could be any of these points. And now it's saying if P moves along all of the points, the locus of all the points it could be, so you can see my P is moving kind of roughly around, well, it's looking like it's moving in a curve like this kind of thing, kind of swooping around there. If you move P around there, the Cartesian equation of the path it moves in is this. Now we recognize this to be a circle, but that's not really important. What we need to do is show this. So okay, let's do that. So we've got some distance here. So I think we know that this distance here is 16 minus y. If I start up there, 16 minus y is that distance. This distance, again, I need to start here is 5 minus x. And I think, therefore, AP squared is 16 minus y squared plus 5 minus x squared. And I can expand that and sort it out. Don't forget to use positives here when you've got two negatives and you're expanding. You can put that together and you get that. So I think that's the distance AP squared. What about BP then? So this distance here, if I start here, I think is x minus -4, so x plus 4. And this distance here, again, I need to start at the same point, so it's y minus 4. And so I get BP squared is this squared plus this squared. Expand that out, again, be careful with the negatives and stuff like that. Put that together, and I think you get that. So I have an expression for my distance AP, an expression for my distance BP. And now I could square root. I know this relationship here, AP is 2BP. So I could square root these things. But actually, it's going to be much easier if I just match this equation to this one, because I don't want roots. So let's square these two things. To get AP squared is equal to 4BP squared, squaring both sides. So now let's find out what 4BP squared is. So times this one by 4, times that by 4. And now I can say, well, this red equation here must be equal to that blue equation because they're both just constants, right? It's just length, so they're both just constants. So that algebra must be equal to that algebra because they both equal the same constant, whatever this length is, I guess. Okay, so now that we've got that, we can do our usual algebra stuff. Take away y squared from both sides, add 32y, and so on. I think you end up with this, which is looking good. These all go into 3, so divide by 3, looking good. Notice how they've got it in like completed the square x form, so let's do that. Half that number is x plus 7, take away 7 squared. That happens to be 49, which makes this beautifully 100. Add 100 to both sides, and I get exactly what I was asked for. So it turns out my guess was pretty good. P does swoop around here, and in the end it makes a circle with center -7, 0, and radius 10. And so if you're on any point on that circle, your distance to this point is half your distance from this point. So that's pretty cool. Part 2 then, very similar question, very standard for STEP. They're asking a very similar question here. They're just making it a bit harder. So point C has A0, so that's on the x-axis somewhere at A0. D has coordinates B0, where A isn't the same as B, so they're not just on top of each other. And the variable Q moves on a path such that, so the variable point Q means that it's got this point Q that can be anywhere you like. And it moves on a path such that QC is K times QD. So for example, if I put Q there, that distance QC and that distance QD, well, it looks like QC is maybe about 1.5 times QD, is my guess, maybe. And then if I put Q here, maybe it looks like QC is about twice QD, I guess, maybe. So okay, that's fine, except it says that the path of Q is the same as the path of P. So actually, Q isn't over here at all. It goes around that same circle that the other one did, that same circle at center -7, 0, radius 10. So Q is on this circle just like the other one was. And I still have my points A0 and B0, except now I look and I think actually, well, here, QC, the distance QC is less than the distance QD. That doesn't make sense because K is bigger than 1. So actually, QD needs to be smaller in order for this to make sense because I'm multiplying by something that makes it bigger. So this can't be my picture. Actually, I think after a bit of thought, you need to end up moving B inside the circle. So your picture actually ends up looking a bit more like this. Now, this doesn't matter. But in some cases, it might do. Like having a better picture of it in your head might make a difference. In this question, it doesn't really because you just do the whole thing with algebra anyway. But sometimes thinking through things like that will help. But anyway, let's do the same thing. Let's blow this picture up and just look at this section. So this is just a blown up version of the circle, so it goes over there somewhere. But I'm just concentrating on this part because I'm going to do the same thing, right? It's the second part of a step question. I'm going to do a similar thing to the first part. I'm going to work out some distances. So that distance there is just y, which is nice. This distance is a minus x. So I've completed this triangle now. And this triangle, height y, distance here of x minus b. Okay, so I've got my two triangles. I can do some more distances. QC squared is equal to y squared plus a minus x squared. And QD squared is equal to y squared plus x minus b squared. Excellent. Okay, now where am I going with this? Well, I can do the same thing I did before. Again, I can square this equation here. K is bigger than 1, so I don't have to worry about getting anything wrong with a negative here. I can just square everything nicely. In fact, that wouldn't have mattered anyway. Whatever. So anyway, I've got this equation here, so I can say that this red stuff is equal to this blue stuff as long as it's times by k squared. So let's get that blue stuff times by k squared, and now I can say this is equal to this, right? Because this is just a constant again. This is just a number. It's just a length squared. So I can say this algebra is equal to this algebra because they both equal the same constant. Okay, now I'm going to sort this out a little bit. I'm going to move this bit over to there. So that's fine. I'm also going to move this y squared over, except I'm going to then put it together to just have a single y squared term of k squared minus 1. So that y squared moves over to become a minus y squared. And then I factorize out the y squared to get to k squared minus 1. So just pause the video and do that in a couple of steps if you want to, but hopefully you arrive at this thing here. Okay, so now what do I do with that? What do I do with this? Well, it looks a bit like a mess at the moment. Let's just make it more of a mess by expanding out. So I'm going to expand out everything. So again, pause the video, make sure I've got this right, make sure those negatives, particularly over here, are all correct, but I have got it right, so just make sure you get it as well. And now I'm going to do the same thing I did with this y squared, but I'm just going to collapse the x squared terms and the x terms together a bit. So I end up with k squared minus 1x squared in total, and for the x's, I end up with 2a minus 2bk squared. And then the constants just go over here as well. So I've got my y squared term here, my x squared term, my x term, and my constant term. Okay, all equal to 0. Now, this is horrible. I'm not pretending like it's not horrible. It's got, look at the thing I'm trying to get. The thing I'm trying to get is just a and b, a's and b's. This has k's, y's, x's, a's, and b's. I've got way too many things. So I need to get rid of things. If I only had like one too many, if I just had a k and no y's and x's, then I'd be okay about maybe being able to get rid of the k, but I've got, how am I going to get rid of k's, y's, and x's from this? Well, I need more information. And then this is the point where I go back to the picture and you think, well, what does this actually describe, this thing here? This describes, via the distance formula, the Pythagorean distance formula, this describes the locus of points that Q is on, right? It's describing this locus, this circle here. But what is this describing? Well, this is also describing that locus of points because this is just the equation of the circle. So these two things are describing the same thing. Okay? They're describing the same locus of points. So let me just recap that. This via the distance formula is describing this locus, and this via just how Cartesian geometry works is describing this circle, this locus of points. So they're both describing the same thing. Now, what I'm going to do to this for a second is I'm going to rearrange it, and I'm also going to expand out the bracket. Now I'm going to explain why I do that in a second. I'm going to move that 100 over, expand that bracket. That makes it plus 49, which is then going to mess with that. But just make sure you can get that into that. Now, why have I done this? Well, it's tempting now to say, well, look, this is the equation of the circle, and this is also sort of the equation of the circle. I mean, it is the equation of the circle, right? Just in a very weird way, because I've gone about a very weird way to get it. Therefore, this is equal to this. And look, I've got some zeros here, so I can just set these equal to each other. Now, this is a problem. And the reason this is a problem is because when you do that whole setting everything equal to each other, like for instance here, I took this and I said, well, this is equal to the same thing as this is, because those two things are the same. Therefore, this equals this. But the only reason I was allowed to do that is because QC squared and K squared QD squared are just constants. They're just numbers. Like QC is just a length, square it, it's just a number. So this algebra all equaled a single number, which this algebra also did, which meant I could set them equal to each other. Now, the problem here is that this isn't doing that. Like these two things aren't describing a single constant or a single point. They're describing an entire curve, an entire locus of points. So we need a new idea here. We can't just set them equal to each other. And now, let's just take a basic example. Now, before I even finish talking, you're probably telling me, oh, well, that's the line y equals 3x plus 1. Thank you for showing me something in this video that I understand. No, so this is y equals 3x plus 1. But is it really? Why isn't it 2y equals 6x plus 2? Like it could be, right? I mean, it is. This is just as good a way of describing that locus of points or that line as this is. Well, okay, so if this is describing the line and this is describing the line, therefore I can set them equal to each other and solve. Well, okay, well, I can try. I can take this one, maybe times it by 2, put this one underneath it, and take away, and great. Okay, so this is not going to work, right? Like I learned nothing. And that's because I'm not solving for a constant or a particular point. Both of these things describe the whole locus of points, so I don't get anything by doing this. And likewise, if I tried to do this on this, I wouldn't get anything if I just set this equal to this, because they're both describing the same thing. There's nothing for me to find, right? So I need a new tactic. And the new tactic that I use is I say, well, okay, what if we stick with this example? And I said, well, this equation here is also describing this line or locus of points. Could you tell me what A and B are? And like, I think you could, right? I think you can recognize, well, this equation, I just times by 4, right? So 3 times 4 is 12, 1 times 4 is 4. So 12 and 4. Or take this one, times by 2. 2 times 2 is 4, 6 times 2 is 12, and 4. So 12 and 4, right? And let's do that as practice again. This is a curve or a locus of points. It's described via this. But I could also describe it via this, right? I think we can agree now. So what if I try to describe it like this? What are A, B, and C? Try and figure it out. Like I'm sure you can figure it out. It's 2 times 3 is 6. So therefore, I need to times this by 3 to get 6 as well. This by 3 to get 18. This by 3 to get 6 as well. And so it's not the actual coefficients that need to be equal to each other. So 3 doesn't equal 6 and 1 doesn't equal 2. But the relationship between all of the corresponding coefficients does need to be the same. I need to be able to find, for two things to be describing the same curve, I need to be able to find a constant scale factor from each of my coefficients, from each of my terms. So a scale factor of 2 every single time, or a scale factor of whatever this ended up being, 3 every single time, right? Or 6 from here to here. So it's about finding a scale factor between your coefficients. And if that scale factor is consistent, then the two things represent the same thing. So now I have a plan, right? I'm saying, this is the Cartesian equation for the circle. I'm saying that this is describing the same thing as this is, right? So if they're describing exactly the same curve or exactly the same locus of points, then therefore, whatever I multiply this term by to get to this one, I must have to do that every single time. Okay, so what do I have to multiply this y squared by to get there? Well, this is just a 1y squared, so I have to multiply it by k squared minus 1, right? To get from 1 to k squared minus 1, that's just multiplied by k squared minus 1. And actually, I can see this is good, right? Because the x squared term follows that rule as well. 1 times k squared minus 1 is k squared minus 1. So let's look at the next two terms then. This 14 must have to be multiplied by that same scale factor, k squared minus 1, in order to make this. Otherwise, these aren't the same curve. So this must be true, which I can obviously just write as that. And likewise, minus 51 must be multiplied by this to make all of this constant bit, which I can, of course, write as that. And now look what I've done. I've got two equations now. They don't have any y's in them. They don't have any x's in them. They just have a's, b's, and k's, which is much closer to what I'm going for. So let's get these two equations out now. Now this doesn't have k in it, so I'm going to try and isolate k from both of these, because if I can do that, I might be able to get rid of it. So now let's try and isolate k. Well, expand out the brackets, obviously. These are all even, so I'll just divide by 2 while I can. Add the 7, add the bk squared, factorize out the k squared, divide through, and look at this, exactly as what's up here. So that's great. And over here, so again, expand out, minus minus makes a plus. Get the k's onto one side. In fact, I've got them over to this side, so that's fine. Factorize out the k squared, divide through, and amazing. And now k is a constant, which means k squared is a constant, which means there's nothing fancy here. This algebra equals a constant, this algebra equals a constant, therefore this is equal to this, because it's the same thing. So nothing fancy there, I can just go back to my old set them equal to each other thing that I did. Okay, so I've shown this. Last part of the question, show further that this is true. Okay, well, all right, I don't really have much to do here except I could just try and cross multiply. That seems like an okay trick first. Let's just expand that out. I'm not feeling too hot about this. 7 times 51 is annoying. I have done it, it's not that bad, but you could have avoided it by just noticing that there's also going to be a 7 times 51 over here, so those are going to cancel. So you didn't actually have to bother to work out what that was. They were going to go away anyway. Now I've colored in these terms because whenever I see coefficients that are equal, I'm sort of pretty happy about that. I'm feeling like that means that I can maybe group them using that coefficient. So when I move the 7b squared over, I can maybe group that into a 7 lots of a squared minus b squared, right? Rather than writing them out as 2 separate things. And likewise, this 51 I'll move over and then group the a minus the b. Now, why am I doing this? Well, it's because factorizing is basically always a great idea. And now I've factorized this, but I can factorize it more, right? This factorizes to a minus b, a plus b. We've seen this a few times in this program. This is good. This is factorized. What about this? Well, this has an a and a b in both terms, right? This has an a and a b and an extra a. This has an a, a b, an extra b. So I can factorize that to be ab, a minus b, I think. Spare a here, spare b here, taking away. And now I've colored these red because look, once you factorize that as well, like I said, you've got a common a minus b term across all 3 things. So this becomes a minus b into 7 a plus b from that first bit, ab, and minus 51. And now go back to the question. Either this is 0 or this is 0 if they're multiplying to make 0. But when we go back to the question, a isn't equal to b. So rearrange and a minus b isn't 0. So this isn't 0, which means if I'm multiplying by this and make 0, this must be. So that there must be 0 now. Okay, well, let's copy that there. We're almost done with this. I don't really know what to do here, so I'm just going to expand out. Now, once I do that, I notice, well, look, I've got some 7s going on. That's cool. Okay. Now I've got a 100 over here. So let's just get a 100 over on the other side. Let's add 100 to both sides. Just because I'm trying to match this kind of thing, I think. Now, if I add 100 to both sides, minus 51 plus 100 is 49. And now suddenly my jaw hits the floor. Because looking at this, it's maybe you don't recognize it immediately, but actually that's going to factorize perfectly. It's going to factorize perfectly into that because there's the AB term there, there's the 7A's, there's the 7B's, and there's the 49. And I end up with exactly what was asked. So yeah, really lovely question, that one. That thing about the curves, the 2 curves describing, or 2 ways of describing the same curve, therefore you find a scale factor between the coefficients. Really important skill, not talked about much in A-level maths, but probably will come up at some point more in your step questions. So yeah, watch that part of the video again if you want to. I think you're going to need to use it again at some point. Really nice piece of maths, that.